Thanks very much, Mike, and thanks very much everyone for the invitation. Really great to present here. So I'm going to talk about Minviro, the history, where we've come from, what we're trying to achieve, our vision for the future within, our vision for the mining and metals industry as a whole. And I'll give you a bit of a crash course in life cycle assessment in the process as well. It's the approach that our business is based on, and really is this sort of the function of how we quantify and mitigate environmental impacts for the mining and metal sector. So I'm going to give a few case studies and examples, but first an introduction to Minviro. I'll give different examples for different materials of interest, so hopefully one of them will be of interest for you. So I'll look at copper, lithium, graphite, and then sort of how this all actually, makes a difference to a downstream product, being a battery. Something that's very important today because extremely rapid development of battery gigafactories, and the raw materials required for that is enormous. And the understanding the impact of these raw materials, whether it's produced in one location through one production process or another, is really quite important to make sure that we're not sort of offsetting the benefits achieved from low carbon technology with high impact primary extraction and processing and refining. And then I'll give a bit of a example of one of our products, which is Mine LCA, and then happy to take questions and answers as at the end. Also, as there's not too many of us, I'm happy for people to jump in with a question and just call out and go through something if there's a particular question that you have. So Minviro is a spin-out company from University of Exeter Camborne School of Mines in the southwest in Cornwall. My background is really as a geologist initially, and I'm sure I attended some Min-South events during my undergraduate days in the summer holidays and some other times. So I studied geology at University of Birmingham, but I grew up in Kent. So I was always at the sort of Min-South events earlier on. So as I said, my background's in geology, and then once I finished my undergraduate, I worked as assistant editor for international mining. So I got to see, how mining operations work in different parts of the world. Saw some very interesting operations and projects and how different technology was deployed. After that, I started my PhD at Camborne School of Mines, and that was really focused on how to quantify the environmental impacts of rare earths, and especially focusing on during the different engineering study, like technical reports, so pre-feasibility, feasibility, what's the type of data that you can extract from that type of engineering study to predict what the environmental impact of the product's going to be, and what data can you use to make sure that you're minimizing the impact if it actually goes through to production and operation. So formed in 2019, that was just me at the time, and then you can see in this picture on the right that it was Lawrence Teisling who was the first hire. He was previously a engineer in the DRC at some cobalt operations, and also worked with some industrial minerals. Now we're actually 9 in London with a couple of people in the US, and looking to expand internationally this year, so we're growing quite quickly. We're both a consultancy and technology company, with our aim is to integrate life cycle thinking into mining and raw material value chains. And you'll see why this is so important with the examples that I give today. I'm sure everybody knows, mining really has a, rightly so in certain cases, but sometimes not, a sort of PR issue. And it has a bad reputation when it comes to sustainability. And I think part of that is, part of sort of like the modern mining industry, a requirement is to really incorporate sustainability aspects even before, right at the engineering point. So as early on as possible, you've got to think about what possible environmental consequences could occur from different engineering or process flow sheets, different, mine designs, different pit shapes, all sorts of things. So, and the reality is all projects are iterations, they've all got opportunities to lower their impact, and so that's a real opportunity. So we work with a range of these companies in different development stages. So whether it's junior mining companies looking just to understand where they fit compared to peers for the environmental impact of the product, we work with large multinational operators looking to quantify their impact, but also looking to maybe plan some impact reduction. So a third of these large mining companies now have committed to net zero by, I think it's 2030 or 2050, sorry. So there's a long way to go to get to net zero, and we can support them in understanding where the sort of the levers to reach those goals are. So I talked about life cycle assessment. That really is the basis of all our work. So it's an internationally recognized approach to quantify the impact of a product or process. It has its own ISO standards. It's been a little bit more established in other sectors. So, in the construction sector, for example, LCA has been sort of widely adopted and in the form of creating environmental product declarations for particular products that can then be used in a building. The mining and metals industry is a little bit further behind, but it's catching up quickly. There's been a really rapid adoption of life cycle assessment, especially in the battery materials and technology materials value chain. And what we try and do is we try and make this approach and the results very clear and actionable and easy to understand. And as I said, I've repeated this a few times, but really is, the first stage is quantifying the environmental impact, and the second stage is looking at, what are the mitigation opportunities. So you can see on the left, on the right here, sorry, the basic approach is you're capturing all material and energy flows into a system, and this system, for example, you can see here, it's looking at extraction, so that might be an open pit or an underground mine, and then a chemical conversion facility, and then maybe this is a transport to the customer over the main product, which might be, say, a copper concentrate or something. And then a co-product, because you obviously need to allocate the impact across the products. And then you're also capturing the impacts of all the emissions, whether that's to air, land, or water as well. So in a nutshell, that's the life cycle assessment approach. Now it looks nice and simple there, but it can get quite complex once you've got a number of flows. It can get quite complex, especially when you're sort of going right through the value chain from a mine to a battery, and you've got multiple process routes, multiple flows of data all over the place. So you can see this is, you may have heard of the different scopes of emissions. This is kind of looking how you draw the system boundary. Usually when we do these life cycle assessments, we're trying to quantify the impact of the products that are produced from a facility. So that might be 1 kilogram of copper, or 1 kilogram of copper concentrate, or 1 kilogram of lithium hydroxide, or whatever it might be, but that would be known as a cradle to gate study. So you're doing it from the mine, from extraction from the earth, which is the cradle, and the gate being a defined sort of end point. Now you can include the use phase of that material, and then even the end of life. So that would be cradle to grave, if you're taking into account that full life of that material. And this is sort of just looking at that sort of relationship there. You can also just do individual you could look at a refinery by itself, and that would be a gate-to-gate study. And then you may have heard about the different scopes of emissions, so scope 1, scope 2, scope 3. Now the scope of emissions isn't actually life cycle assessment language, it's actually the greenhouse gas protocol that defined this. And I have a few qualms about the way that the scopes are defined, because it kind of is a bit confusing for the generalist in terms of scope 1 and scope 2 is pretty straightforward. Scope 1 referring to direct emissions that are on your site or within your system boundary. Scope 2 is indirect impact related to production, purchase, and consumption of energy. So any electricity, the embodied impact of producing that. And then scope 3 you can think of that in upstream scope 3, which is the embodied emissions of, say, reagents and chemicals. And then downstream scope 3 would include those points that I mentioned, which is like the use phase of that material or the end of life. So that's really kind of the scopes of emissions. But life cycle assessment isn't just about climate change. It's about a broad range of impact categories, and global warming potential is very important. Everybody is, clearly has that as a priority, but there are another, dozen or so impact categories that can be equally relevant. So you can see ozone depletion, human toxicity. So for example, if you have organic flows, emissions going into the land or water, then that can have a significant impact. Particulate matter. So if you've got a lot of sort of PM 2.5 emissions in a dense populated area, then that's going to cause high disease incidence rates, radiation-related impacts, photochemical ozone formation, and you can see some other ones like acidification, eutrophication, land use-related impacts, water use, and resource use. So I'm going to skip through this because I don't think this is particularly, we can go back to that if that's of interest to people at the end. That's kind of just looking at the specifics of rare earths. That was part of my PhD, but I'm just going to sort of show you what our common consultancy type work output looks like. So you can see, we deliver ISO compliant reports. It also often includes benchmarking, so companies can see how they compare against their peers in terms of environmental performance. We often do scenario analysis, which is a company comparing scenarios for their project. A prime easy example to think about here is, does a company choose to invest significantly in, say, an electric fleet at the mine site versus using just a diesel fleet? What's the scenario? What's the environmental impact of those different choices? And then obviously there's some technical ISO compliant requirements like data quality and uncertainty analysis, because with any model, the quality of the data going in also dictates the quality of the results going out. And so we have to make sure that we're doing some sort of analysis on that. And then the review process. So in order for it to be an ISO compliant LCA report, you need that third party review, and we really make sure that that's done to the best quality. So you can see on the right here, this is the example of the results output. So you can see the relative contribution to the climate change impact category in kilograms of CO2 equivalent per kilogram of copper in concentrate. And you can see underground mine at about 2 and the concentrator at about 2. So about equal there. You can then dig into this into a bit more detail and see exactly what is contributing to those impacts. So you can see some explosives in the mining, some diesel, some propane, electricity, and other consumables. And then in the concentrating, you've got grinding media, flotation reagents, but a majority coming from the electricity. So life cycle assessment includes some, these sort of stages. So goal and scope, this is where you're defining what you want to measure, what you want to get out of the study. And then the life cycle inventory, which is basically all the material and energy inputs, which I was talking about, as well as the emissions. And then the life cycle impact assessment, which is converting all that inventory into those different impact categories using characterization factors. So this basically the whole life cycle assessment approach is just very data intensive, lots of databases, lots of background data, and then a big phase of LCA and differentiating between a good LCA practitioner and maybe not such a good one is the interpretation phase. So I suppose one of the differentiators with Minviro is that we are all mining, mineral processing, chemical engineers, geologists as background. And so, we really sort of understand we can do good QA, QC on what the data models that may be provided by the clients, or if we're building from first principles, we can do some comparisons against data from one model to another to make sure that the life cycle inventory makes sense, and therefore the life cycle impact assessment makes sense. So now we can do a little run through of a project with some scenario analysis and see what the results look like. So we can look at again, this is that same project I was showing before, looking at 1 kilogram of copper in concentrate. You can see all the material and energy inputs here. You can see all the emissions on this side, and you can see the high-level processes which are including in this study. So anything in this dotted line is considered to be within the system boundary and is included in the measurement. So we're looking at the impact of the underground mining, we're looking at the impact of the crushing and grinding of that material, the gravity separation, the copper flotation, and you can also see that you've got gold concentrate which is coming out of the gravity separation, and then copper concentrate which is coming out of the copper flotation. You can see a few details here. So we're looking at an underground mine in Russia, 60,000 tons of copper per year, 35,000 ounces of gold in concentrate per year. You can see a few other bits here. So we're doing some scenarios with different electricities going in. We're also doing a scenario analysis for electrification of the mining fleet in the underground mine. And so for these 3 scenarios, we're looking at electricity from the Russian grid and heat from propane as the base case scenario. We're looking at electricity and heat from natural gas with a combined cycle turbine. And then for the third scenario, we're looking at electricity from hydropower and then heat from propane. So I've talked about these results, so I won't talk about these for too long. You can also see the results here we've already spoken about these, so you can see the contribution of those impacts. A bit more detail about these, but you've already seen that, so that's not too interesting. And then we can look at the scopes of emissions. So I defined the scopes of the emissions previously, and you can see scope 1, 2, 3, and exactly whether that's in the underground mine or the concentrator. So you can see a majority of the impacts are actually in the scope 2. So from a view of then as the company, you can say, well, the biggest opportunity lies in the energy that we have for the project. The purchased electricity. If we can get that from a different supplier or lower that impact, that's probably going to be the biggest opportunity. So this is why you would want to know the scopes of emissions to sort of direct you. Cool. So now we can look at some scenario analysis. So these are 3 scenarios that I described earlier. So base case with the Russian grid, and you can see that that's around 4.5 kilograms of CO2 per kilogram concentrate. Then with this combined heat and power, natural gas, you can see the contribution of these scenarios, and you can see that's dropping down below 4. And then the hydropower, you can see significantly lower impact per kilowatt hour of hydropower electricity. That brings that right down. So you can see significant opportunities for impact mitigation there. Now, interestingly, in the base case scenario, if we look at the comparison of the electric fleet versus the conventional sort of diesel fleet for underground mining, you can actually see that the electrified fleet on that Russian grid has a negative impact because the background energy system, the electricity produced in that part of Russia, is coal dominant, and so has a very high kilograms of CO2 per kilowatt hour. So this is why it's important to think from a life cycle. It's life cycle thinking. Just because something sounds like a sustainable, lower impact solution, it needs to be quantified in terms of environmental impact. And so these are all those scenarios put together. I think you can see it's quite clear that the optimized scenario would be an electrified fleet, but with hydropower as an energy source. Now, this isn't saying that this is like practically possible or technically feasible, but this type of analysis really can help direct companies in how they're going to achieve certain targets. So I've given you a very, very simple one initially, but this can get a little bit more complex and sort of more related to geology and grade and geometallurgy, I suppose, a little bit more. So this is a temporally explicit life cycle assessment. So if along the x-axis we have time, and then on the y-axis we have kilograms of CO2 per kilogram of metal in concentrate. And I believe this was actually a nickel project. And you can see the bars are showing obviously the total value is the cumulative impact, but then you have the contribution by different inputs, and you can see you've got transport, diesel, reagent, ANFO, and power. But you also have a credit from a byproduct that's being produced from this mine site. And then you also, laid on top of that, you have sort of the volume of kilograms of metal produced in kilograms. So what you can see here is that the impact is not consistent. So although we get a metric, which is like kilograms of CO2 per kilogram product, that's an averaged value. The reality is it changes a lot, and that's because of changing grades, changing processes, even changing electricity source or background availability of different things. So all sorts of things can change at a mine site. And you can see that this ranges from around 4 kilograms up to 21 kilograms at its highest. And then you can see that the biggest contributor early on is the explosives and the diesel. And then, as the mining stops, you're starting to end the mining and you're just using some of the processing at the end here. That's sort of, obviously you need to use any explosives if you're not doing any mining anymore. So you can see that that's sort of ending there. And we explored this a little bit more detail. So that was really very simplified geometallurgy, but it can get much more complex. If you're starting to look at ore, minerality, character, penalty elements, other characteristics that can dictate sort of material and energy requirements, then you can start to build out these quite complex models. And we published this paper in Nature Reviews Earth and Environment, looking at integrating life cycle assessment and mine scheduling and geometallurgy together. Happy to share that with anybody that's interested as well. It's looking at in the context of battery and technology materials as well, all that. But you can see basically what this it's like an iterative process, taking in all the data that you have, adding more and more data about the deposit. And the reason this sort of came up, we built this on the back of another academic study that we did a while back, Lawrence Teisling himself, on integrating life cycle assessment with mine scheduling. So you can basically define certain characteristics per block that will dictate the life cycle assessment impact. So, and then you can model that. So you can optimize the pit based on carbon intensity. So that's really interesting, and happy to talk more about that if people are interested at the end. We've actually got a recent press release with MapTech, combining our Mine LCA tool with MapTech to basically look at the impact of different mine scheduling scenarios. Cool, so now I'm going to go on to some battery materials. So we can start with lithium. So one of our, I suppose, our early fame was in the lithium sector. So we published a white paper doing the first ever life cycle assessment of lithium hydroxide on a hydrate, comparing different production routes. And so this is really that study. So you can see two scenarios from the lithium triangle, one from lithium brine in Chile, one in lithium brine in Argentina, and then spodumene from Australia being converted to lithium hydroxide in China. And you can see roughly these are the flow sheets there. And this is it's obviously there's a white paper on this as well, which is publicly available. So I'm happy to share that with everyone afterwards. But you can see that depending on the production process and the region and all this data, it really makes a significant difference. So Chilean brine impact is around 5 kilograms per kilogram of product, and then Australian product spodumene source is 3 times higher. Now, this really makes a difference if you're a battery manufacturer and it actually, material makes a difference about your business model, whether you purchase your material, your lithium from spodumene versus brine. Now, it hasn't historically, but there's a lot of regulatory change that's going on. So, for example, within Europe, there's a regulation which has been tabled to have a carbon footprint requirement in batteries, and then companies are going to be basically tiered based on their impact of their battery. So, that's getting more and more important, and so this is why this impact of these different battery materials is so important today. So I talked about impact mitigation, and we sort of looked at some scenarios before, but this is another output, that we can get. So we might do a life cycle assessment for a base case scenario. So you can see on the left, this is where the impact lies for a pre-feasibility study, sort of engineering report. And then we worked with a company to model a load of different scenarios that you can see along the x-axis here. So we can see the impact reduction opportunity per kilogram of product from the solar electricity at the mine site or solar electricity at chemical refining. And then you can look at replacing natural gas with hydrogen in the roasting. So you can see all these scenarios where you can model to see what kind of impact you can actually get to if you optimize your project for all environmental performance metrics. And again, this is very useful during the pre-feasibility studies because you haven't committed millions or hundreds of millions of pounds in infrastructure, which means that you can't change things. You still have an opportunity to change direction and change processes as you move from pre-feasibility to feasibility and through to operation. Cool. And then another key material for the battery is graphite. So graphite, again, was a very opaque material, as in nobody really knew what the impact of battery grade graphite was. So I have, anecdotes of European regulators and PEFCR, so the product category rules for battery, actually using carbon black as a proxy for battery grade anode, and it's just not the functionally same material, doesn't undergo the same processes, doesn't have the same embodied impact. So again, we kind of wanted to just blow the lid on it, show just communicate to the world that the impact of battery grade graphite being quite significantly underestimated. So again, we published a white paper, a couple of white papers on this topic. And yeah, I've really been working with a lot of graphite producers to try and reduce their impact. So one of the big issues with graphite is a significant amount of the energy intensive graphitization process occurs in Inner Mongolia, in China. And the reason why it occurs there is because it's extremely energy intensive. And the reason why they chose Inner Mongolia is because the electricity there, or energy, is cheap. And the reason why the energy is cheap is because it's plenty of coal. And obviously that has an impact because that's very high kilograms of CO2 per kilowatt hour or per megajoule of energy. So graphite really does have quite a significant embodied impact, and there's quite simple solutions to try and reduce that. So I think we'll see a lot of activity in the graphite space over the coming years. And again, you can see sort of the comparison. So these are the commercial databases that existed before we published our white papers and showed that the impact had been quite significantly underestimated. And then you can see these are the Chinese sort of scenarios, 8 times the baseline for natural graphite, and then around 10 times for synthetic graphite. And again, this is a white paper that's publicly available. And so what does this mean for batteries? So we also published a white paper looking at NMC 811 battery chemistry. So one of the sort of nickel-rich chemistries, high performance batteries. And what we did is we created a static model other than changing key material inputs. So nickel sulfate, cobalt sulfate, manganese sulfate, lithium hydroxide, and anode grade graphite. And you can see that the impact between we basically looked at representative low impact production routes for those materials and representative high impact production routes for those materials. So this isn't the lowest or the very highest that could ever be achieved, but it's sort of highlighting the range. And you can see, it's around double the impact whether you choose high impact raw materials versus low impact raw materials. And what we titled this white paper is Shifting the Lens, because so many gigafactories, so many battery manufacturers are really focusing on decarbonizing the electricity in the manufacturing step of battery manufacturing. But the reality is all the impact is embodied in not all of it, but a significant proportion of the impact is embodied in the raw materials. So it's talking about, shifting the lens, understanding that raw material impacts really matter. And this basically proves that. You can see the range of impacts, whether you're getting it from low impact raw materials or high impact raw materials. And to give you context of why this matters, so we did some back of the envelope calculations on what this means for the sort of scale of battery manufacturing globally. And if companies accept these higher impact raw materials over the next decade, then the cumulative impact of those choices between that and the low impact raw materials would be the same as 3 times the annual CO2 emissions of the Netherlands. So these aren't trivial amounts of CO2. These are significant impacts, and that's just for the climate change impact category. So this is true for a broad range of impacts. There's a load of, in the questions afterwards, we can talk about a lot of different challenges within the battery material value chain, but there's different trends going on. Say nickel sulfate coming from Indonesia, again coal dominant region. Lots of different trends going on, which could significantly have impacts on the battery materials. And then this is our Mine LCA tool. So it might actually make more sense if I just open up Mine LCA, go through this in person, because I think that would be a bit more interesting. So basically, this is our online Mine LCA tool. It's designed to be used by pretty much any mine owner, engineer. We really didn't want to have somebody with significant life cycle assessment knowledge or even environmental knowledge. We basically want this to be embedded in decision making. This is the home page. You can look at some previously saved projects. You can see that you can categorize them if you want. Maybe let's just have a look at this one. So the data in here isn't realistic, but at least we can sort of show you how the tool works. So you can very easily see from the top level what's the contribution from mining, what's the contribution from crushing and grinding. So we can dig into there. We can see waste rock management, extraction. Again, we can dig into there, see exactly what's contributing. So we can see there's some direct emissions there. We've got some steel and stuff like that. We can also look at the different impact categories. So I mentioned those. We can see, is human toxicity the same? You can see it's pretty much all in the extraction here, and it's pretty much all coming in the steel. That's actually, but it's a very low impact here, so that's not necessarily that useful. We can also look at particulate matter. That's pretty much all in the mining, all in the extraction, and then, as you'd expect, it's actually all in the use of explosives. So that's pretty obvious. What's quite neat about this as well is we can minimize impact. So you have your baseline scenario, and I'll show you how you model that in a bit, but you can very quick, with a click of a button, see the major contributors to your impact. So explosives here, and then you can see what alternatives exist. So you can get a different supplier of this explosive, maybe an emulsion mix or something, replace that, maybe change the electricity source. So maybe we're looking at the grid mix and changing it to, say, a wind turbine. And then again, just with a click of a button, we can recalculate that impact. So this is basically doing this whole life cycle assessment, and you can see exactly what the impact reduction is. So you can see a cumulative reduction that goes down from 16 to around 10.5 kilograms per kilogram of product. So this is a really powerful way of simulating scenarios to reduce your impact of your project. And a lot of the work that we've done is integrating this with other technology. So I talked about map tech, but there's other, working with operators, we can connect to ERP systems. So if they've got purchasing data for their diesel, whatever, their electricity consumption, they can just connect with this automatically and then see how they're performing month on month or even week on week. Maybe I'll just show you what this looks like and if you're manually inputting data. So very simple, just put in the project name, you identify what stages you're including. You can put some information about where your project is, for example, Australia. Then this is, you can actually, if we delete this, you can see that there's all different sorts of Australian specific electricity. So we can even go by region. So we go Queensland, for example, here. We also have a latitude and longitude. I might show you this because it's quite cool. So let's find the London longitude, latitude. So 51 to 52. And then I think it's that. There we go. So we've got London. Obviously that doesn't make any sense because we've done it. We've said it's Australia, but then we're putting the longitude and latitude in London. But we're going to transport this to, so this is in the mining phase, and then we also put this into Melbourne, maybe. So basically, we've got an embedded transport impact calculator. So if you're moving material from one location to another, it's calculating the impact of that transport. So you can see we can go into these previous scenarios. We can add more data if you want, add more inputs. Like we can put some concrete in there. Just update that. And then we can just generate this report again. So then we're just running the life cycle assessment model with those inputs. And the transport impact calculator is really good because if you've got multiple stages of material going from one site to another, and if you've got a vertically integrated model, then it's important to understand what the impact of transporting everything is. So we've got that inbuilt. It might take a little bit longer to load this report now because it's simulating that commercial transport route. But you can see this is the same results as we had previously. But we can see the transport is pretty low. I mean, I think this is probably, yeah, I'd obviously put in a lot of concrete there. So that's obviously made the results a bit silly, but you can see, if we zoom into here, wait, I'll go back and edit this because that'll make it easier to see. I think it was in this section. So, well, no, it was in the next section, wasn't it? I'll just delete that one, update that, and then generate the report. And you'll see that, so the transport, it gives the whole impact, but it also actually gives you the impact by stage. So we go in here, now we can see the transport, and we can see that the impact of transport to port, port to port shipping, and then transport from the port to the final destination. So you can see at quite high resolution exactly where the impact is coming from. Cool. Go back to this presentation. So we also have, I won't go through, but we also have Minviro, which is a similar tool, but it's designed for battery manufacturers so they can design their full supply chain. And again, just some of the features that we have there, some of the things that we can connect to with this tool. And I've shown you this, so you know. And then finally, before we could sort of go to discussion, it's just, you know, everyone, we work with a number of different stakeholders. So we work directly with the mining companies. We work with engineering firms who are looking to sort of, you know, they want to offer the lowest impact engineering solutions to the clients. We also work with investors. So investors want to either do due diligence, make sure they're not investing in what's going to be maybe a stranded asset or going to have risk associated with its environmental impact. So you can see a few different ones there, but we also work with the downstream as well. So battery chemical buyers, you know, other technology metal manufacturers, so OEMs and stuff like that. And you know, the last thing is like it's really key that we understand the impact of all the raw materials that are entering the economy today, because you know, at the end of the day, the embodied impact of those materials is going to dictate how low impact the technologies that they go into are. Just a couple more bits on that. That's the same paper that I mentioned earlier. So again, if you want to look more into that, happy to share that with you. And then just a little bit on the team. You obviously see me. I spoke about Lawrence earlier. Phoebe Wattoff, who completed a master's in carbon sequestration. So she's worked on some interesting nickel projects, looking at what's the opportunity to sequester carbon in tailings. Then we have some of the lithium partners. We actually don't have everyone on here. We've got a few more people since this has been updated, but then we've got our technical team and some of our connections from University of Exeter. Cool. Happy to take questions.